So the first couple of days of this unit are, well, especially today, seems probably pretty straightforward. Monday, again, will be fairly straightforward, but there's some important connections to make. But then Tuesday, all of a sudden, is quite a bit more difficult in some ways. So keep that in mind. And one of the things that we talk about is domain in particular, domain and range, but really domain is the one that we focus on. So what we're looking at is combining functions. And in the real world, so when you start looking at functions in grade 9 and you're looking at linear functions, linear relationships, pretty simple stuff, right? You can buy a basket for $12 and fill the basket with items for $1 each. And there's your linear relation. And things in the real world certainly work that way, but it's fairly basic. Grade 10, you introduce quadratics, and then grade 11 and 12, so far we've introduced a lot more. But still, if you were doing a lot of this stuff, anything complicated in real life, it likely would not follow a simple, one simple function, okay? So to model things in real life more realistically that are impacted by gravity or air resistance or that kind of thing, you're probably going to use some combination of functions. And so we only get a small taste of it, but that's what we're looking at is what happens when you start combining functions. So you're going to see the first example we're going to look at works out very nicely, but then when you start to expand this, it could get messy, but it gets very powerful as well. So when you're adding two functions or subtracting, you are literally adding the y values for the same x values. So you go over to where x equal to 2. Like if you're thinking about this graphically, you look at the two functions and you find the y value for both functions when x equals 2, add them together, and that's the y value of your new function. Literally, that's what you're doing. And algebraically, you are also literally just adding the two functions together. So it's fairly straightforward. It's fairly intuitive. Think about this, though. You could only add the two functions where both functions exist, in the domain where both functions exist. So we're going to look at a quadratic and a linear function, and they both exist everywhere, right? This is something we know about polynomial functions. They exist, their domain is x is an element of the real numbers. So my domain will be simple. But functions like the logarithmic function or the square root function or different things like that don't exist everywhere. Their domain is restricted. And so if you're adding them, you can only add the two functions where both of them exist. Okay, and that goes for subtraction as well. Some of what we're going to look at in this unit as well is notation. Again, the notation will be fairly simple for today and Monday, but Tuesday is something that you need to get the notation in order to be able to successfully do the material. So keep that in mind. Notation is a little bit new here. Okay, so let's take a look at example 1. We've got function f at x, which is a quadratic, and g at x, which is linear. So we have to determine the equation and the graph for each of the following. So let's start with A. And I'm going to graph the two of these. This is really good practice because, we've graphed all kinds of things and it's all fair game on the final exam that's coming up. So anything you've ever graphed in all of high school math could come up here kind of thing, right? So quadratic hopefully is easy. What's going on in that quadratic? It's got a reflection in the x-axis that opens downwards and it's shifted up 1, otherwise it's normal. So 1, and there, and here, and then there, and there. Don't rush through this stuff. If this comes up on the exam or during this unit, don't rush through. I find it because we are worried about the new aspects of this. We make mistakes in the easy stuff. So don't rush through your graphing. Don't take it for granted. Make sure you do it correctly. That's from experience. That's because I notice I do those things sometimes. Okay, and the next one Starts at 0, 4, and 8. And then negative 4 and negative 8. Okay, so there's our graphs. So let's see, which one's f at x? This is f at x. For this, for part A, it doesn't really matter which one's which, because when you're adding f at x, so f plus g at x is the same as f at x plus g at x, right? That's what that means, that notation. F plus g at x, f at x plus g at x. And f at x plus g at x is the same as g at x plus f at x. Same thing. That might seem like a weird thing, but it'll be important in a minute. So it doesn't really matter which one's which. So I'm just going to add. And here's what I'm going to do. I'm going to look for key points, easy points to add to get a sense of what's happening here. So this one is 4. Can you see what I'm doing here? This one's, 4, and this one's 0. So that's going to give me a point there. And let's see, this is negative 3, and this is 8. So that's going to give me a point here, right? 8 minus 3, 8 plus negative 3 is 5. So I have a point at 5. I have a point at negative 4 plus 0. So that's negative 4. 1 plus 0 is 1. And this point over here is off the graph, but I know what it is. It's 12. And I know that this one is 8, so 12 minus 8 is 4. So I should have another point here, 4. There's not really a rule about, like, you know, well, how do you know you're supposed to get points from off the graph? You're trying to get a sense of what the graph looks like. What does it look like it's going to be? Parabola. And you're right, it is. And when we think about it algebraically, we're going to understand exactly why. So there it is. Okay, there's my graph. Does that make sense? Of course that makes sense. Think about what this is. This is negative x squared plus 1 plus 4x. It's a parabola. It's just a regular parabola. There's nothing fancy about it. That's why this, like, really, when you look at that trinomial, you can think about how every parabola you've drawn in that sense is like a parabola plus a linear function. We just didn't think of it that way. But we've always been adding quadratic things, x squared, to linear things, x, to constant things, 1. Like, we've been doing that forever. So it's the same thing. We just didn't think of it this way. That's why today might seem kind of simple. It's sort of just stuff we already know. Now, what's neat is if I complete the square, I get x squared plus 4x. So half of that is 4. So plus 4 minus 4. Oh, sorry, this should be negative. So that should be negative. So that should be positive plus 1. So this works out to negative x plus 2 squared plus 5. So that's got a shift to the right 2, opens downwards, and has a vertical shift up 5. That's the parabola that we just drew, right? See it algebraically. Yeah. Yes. Well, I should have factored this out. Thank you. This should be negative. Okay, let's take a look at B. So f minus g at x is f at x minus g at x. Whoa, I'm going to run out of space here. So order does matter here. F minus g is not the same as g minus f. 2 minus 3 and 3 minus 2, not the same thing. Similar, but not quite the same. So which one's f? F is the green one. So I do the same thing. I'm just going to pick some points. And I'm going to make sure I'm subtracting the right direction. Okay, let's try blue. So this is the green point, which is here, minus 0. So that point is still there. This one is 0 minus 4. So that should be negative 4. This one is 0 minus negative 4, which is 0 plus 4. So that should be 4 there. And remember what we said at the very beginning, you find x points, like points above each other, right? So you're adding the y values of the same x values together to get your new function. This one here is negative 3 minus negative 8. So negative 3 plus 8, which is 5. And we can keep going, and you'll see that we're getting another parabola, which makes sense algebraically when you think about it. Whoops. I knew that looked weird. I missed 5. That's better. Okay, and algebraically, this looks like negative x squared minus 4x. I'm just going to write it in the right order, plus 1. So if I factor out the negative, I get x squared plus 4x plus 4, and then plus 4 plus 1, which is negative x plus 2 squared plus 5. So that one's a shift to the left 2, and up 5 opens downwards. That's the basics. Any questions about that? Okay, if you don't have this graph, if you didn't print out the lesson, don't worry too much about it. You can just watch for a graph like this. We're not going to do much like this, but it's kind of interesting to think about. What would I do? Again, I would find common points. So this is like 3. Oh, I'm adding them together. So 3 plus negative 8 is negative 5. And this is 1 and 0, so that should be 1. And this is what? 8 minus 1, so 7. And really the points that you're worried about is anywhere that, in this case, like if you had strange graphs or like parabolas or a sine curve or something, it would be really hard to do this. You would just have to estimate, which we'll see a little bit of. But if it's straight like this, anywhere the graph changes, that's where you want to make sure you add those values together, because between them it's just going to be a straight line. Okay, so let's see. This is negative 4, and this is 7. So 7 minus 4, 1, 2, 3, 4. So there's going to be a point there. There's going to be a point. This minus 1, so here. These added together is 4, and these added together, let's see, that's negative 2, and that's 2. So it's going to look something like straight line, down, up, and then there. That should be kind of straight. And then stops, because the red one keeps going in both directions, but the blue one doesn't. So when I add them together, the new graph only exists where both graphs existed. Does that make sense? Any questions about that? Just look for key points. Pretty easy. Algebraically, sometimes it's very easy. It just gave us a quadratic. Sometimes it's not going to be as easy. Graphically, we understand what it means. Determine the domain. Here's a trickier question already. Of f plus g at x. If f at x is log of x plus 3, and g at x is negative the square root of 2 minus x. Anybody have an idea about how we're going to go about solving a question like this? Alex? Yep. Right. And then what? In other words, what are you saying? What should we start with? Which is another way of saying, like, state their domains, right? Like, we want to know the domain of each of those, because then we know where they do exist and where they don't exist. Okay, so let's do f domain. How do log functions work? This is a good review for tomorrow, Hunter. Is that a hand up? Go for it. For log? Remember, it's the inverse of an exponential function. So if you can think of the range of an exponential function, that's going to be sort of the same as the domain of the log that goes with it. Graph one, like sketch it. What's the transformations in there? Even if you don't know what a log graph looks like, you should be able to look at that and understand what the transformation is. This is the kind of stuff that the exam's going to be about, like all kinds of different things thrown at you, all scattered, and you have to figure it out. Zoe? Yeah. So that's what a log function looks like. It has an asymptote doing this, but it's moving left 3. So it exists forever up and down. Y is an element of the real number. We're not talking about range, but right? Y, it can be any Y value that it goes down forever and up forever. And this one will go to the right forever. It'll keep growing to the right. But it has an asymptote that it never crosses on the left for this one. Okay, so it's going to be x is an element of the real numbers such that x is greater than negative 3. Not greater than or equal to, it's an asymptote. G domain. X is an element of the real numbers such that, oh, this one's a bit harder. I'm going to go over off to the side somewhere, get rid of some of this. Let's see, g at x. What do I have to do to figure this one out? Factor. So negative square root. Factor out, it's like negative x plus 2, so I factor out the negative, and then it's x minus 2. So it's got to shift to, and what does a square root function look like? Starts here and goes like that. It's a parent function. This has a reflection in the x and a reflection in the y, and then a shift to the right too. So what it actually looks like is something like that. And what does the other one look like? Something like this. So complex overlap. It has a bound on either side. And anything could happen here, right? Like there's any combination of different kinds of domains that you could be overlapping in some ways or other ways. So this one is x is less than or equal to 2. So then f plus g domain, x is an element of the real numbers such that negative 3 is less than x, which is less than or equal to 2. Where they both exist. G at x exists starting at 2 and goes forever to the left. But f at x is bounded on the left. G at x is bounded on the right. So, everybody okay? Whoop. Ooh, this one's a tricky one. So I have to add these two together. Log of x minus 3 plus negative square root of x plus 2. So log of x minus 3 plus negative, so minus the square root of x plus 2. How do I simplify that? You don't. We're done. Some of the questions are kind of trivial. But we don't. You might think, wow, square root is like an exponent and logarithms like that. Yeah, but no, we don't have, we're not. So you could graph that. It would be interesting to see what the graph of that looks like. In fact, I don't know. Oh. There we go. Let's see what that looks like. Log of x minus 3. There it is, log of x minus 3. Uh-oh. Oh, this is going to be hard. Might have to do it after. Log bracket. This is just how GeoGebra does things. Comma. X minus 3. And square root bracket x. What was it? Plus 2? Plus 2. Hope that's right. Oh. Oh, it was negative square root. Oh, jeez. Thank you. And f plus g, doesn't look very interesting. It can be hard to predict. If you think about it, it'll make sense. But what's that one look like? Kind of looks like a sideways parabola. G minus f, not very interesting. I think there was another one here. What's this one? X minus 3, negative x plus 2. Thought there was a better one. What if I change that to a negative? Forget it. Okay, let's do the next example. Determine an equation for g minus f. So again, this one, order matters. Make sure you subtract the whole function. Example 4, trivial, because there was no simplifying that you could do. But this one, absolutely, we can simplify. Don't leave it like this. So 2x minus 5 minus x plus 3 all squared plus 4. 2x minus 5 minus x squared plus 6x plus 9 plus 4. So that's going to be negative x squared. 2x minus 6x is negative 4x, and negative 5 plus 4 is negative, minus 9 is negative 10. Just a bit of algebra. Doesn't seem maybe all that exciting or all that interesting yet, but trust me, it's getting there. Any questions?